Hi, I'm Professor Afshar at Glendale Community College. This is Physics 101, Lecture 14. In this lecture, we'll discuss uniform circular motion. This topic is covered in chapters 4 and 6 of our textbook by Surway and Jewett. In this lecture, we want to discuss circular motion. Circular motion is our second example of important two-dimensional motions. Recall that our first important example of two-dimensional motion was parabolic or projectile motion. We're now turning to circular motion. Circular motion, i.e. motion along a circular path, is an extremely common type of motion found everywhere in science and engineering. Just as an example, a car that travels on a freeway interchange between two perpendicular freeways executes circular motion, so a civil engineer that is trying to design this type of a road would have to understand circular motion. The rotor inside an electric motor executes circular motion, so an electrical engineer that is designing electric motors has to understand circular motion. A roller coaster car going through a loop-de-loop would have to execute circular motion, so a mechanical engineer that is designing a fun roller coaster would have to have a thorough understanding of circular motion. The fan blades of a turbine inside a jet engine also execute circular motion, so an aeronautical engineer that is designing jet engines would have to also understand circular motion. Our goal for this lecture is to develop a basic understanding of circular motion that can be applied to all these examples. Circular motion in general can be quite complicated, so we will begin with a simple type of circular motion known as uniform circular motion. When an object moves along a circle with constant speed, it is said to execute uniform circular motion. So what makes the motion uniform is the fact that the speed is constant. Uniform circular motion has some important properties that we must understand. In this picture, I'm depicting the motion of an object executing uniform circular motion. Each dot represents the position of an object at equal time intervals. So we can imagine that at t equals 0, the object was located here. 1 second later, it's located here. A second after that is here. And a second after that, the object is here. And so on around the circle. Notice that the distance between two consecutive circles does not change. That distance is constant, telling us that the object is traveling equal distances in equal time intervals. That in turn tells us that the speed of the object must be constant, and therefore what we have here is uniform circular motion. Recall that if you want to understand the motion of an object, you have to understand its kinematic variables. In particular, you need to understand its position, its velocity, and its acceleration. For an object engaged in uniform circular motion, the position vector is always radial and has a magnitude r. So these blue arrows indicate the position of the object at various times. All of the position vectors begin at the center of the circle and they point directly to where the object is. Notice each one is radial, meaning that it points along the radius of the circle, and each one has the same magnitude, namely r, namely the radius of the circle. This fact should be somewhat obvious. So maybe what is less obvious is that the velocity vectors are tangential. Remember that in general, the velocity vector is tangent to the path that an object is following. So when the object is located over here, the velocity vector points straight up and it is tangent to the circle at that particular point. A second later, when the object is located over here, the velocity vector is again tangential to the circle. A second later, when the object is over here, the velocity vector points horizontally, but still it is tangent to the circle. Notice that the velocity vector and the position vector are perpendicular to one another. This is an important property of circles in general. The tangent to a circle is always perpendicular to the radius of the circle. Perhaps the least obvious thing about uniform circular motion is that the acceleration vector is also radial, and more importantly, it has a magnitude of v squared over r. The green arrows in this picture indicate the acceleration vectors. Notice everywhere the acceleration vector points along the radius, hence it's radial, but it does point directly towards the center in the opposite direction to the position vectors. Whereas the position vectors point outwards, the acceleration vectors point inwards. The acceleration vectors are radial and they always have the same magnitude. That magnitude is v squared over r. The fact that the acceleration vectors point inward and the fact that they have this particular magnitude is not at all obvious. We're going to have to discuss these two facts at length. But remembering this fact is important. This is perhaps the most important property of circular motion, namely that the radial acceleration is v squared over r, pointing inwards towards the center of the circle. As we stated, the acceleration vector for an object executing uniform circular motion points inwards towards the center of the circle. That fact is not at all obvious. To motivate that fact, consider the motion of an object in uniform circular motion. Specifically, focus on two moments in time. Imagine that at one time, let's say some initial time, the object is located here, and a second later, or some short interval of time later, the object is located here. Initially, the object will have one velocity vector, and finally the object will have another velocity vector. Notice both velocity vectors are tangent to the circle, and also notice that both velocity vectors have the same magnitude because the speed needs to be constant. That's a property of uniform circular motion. Now we're interested in the acceleration of this object, and to calculate acceleration we need to calculate the change in velocity. Recall that the average acceleration is defined as the change in velocity, delta v, divided by delta t. When we talk about delta v, what we're talking about is the change in velocity, so v final minus v initial. What we must do to calculate the average acceleration is calculate the difference between this vector here and this vector here. Since we don't have numbers here, we'd like to do the subtraction geometrically. Remember that to subtract vectors geometrically, we must follow a very specific recipe. We must begin by placing the vectors tail to tail and then connecting the open ends. So I have moved one of the vectors, v final, so that its tail coincides with the tail of the initial velocity vector. And now by connecting the two ends, I can figure out what delta v is. If the time interval from initial to final is just 1 second, then I can say that the average acceleration vector is basically equal to delta v divided by 1. So this simply indicates that the acceleration vector does indeed point inwards towards the center. This argument here says nothing about the magnitude of the acceleration vector. We'll turn to that question on the next slide. For an object in uniform circular motion, the magnitude of the acceleration vector is v squared over r. As we'll see later, this is an incredibly important fact about uniform circular motion, and it is one that is not at all obvious from considerations of circles alone. To prove that fact, we'll have to do some lengthy calculations, which we'll carry out over this slide and the next one. To have a concrete example in mind, imagine a car driving with a constant speed v on a circular track of radius r. You can imagine that v and r are known or given values. To begin with, assuming the car starts at theta equals 0, what is theta at time t? In other words, we'd like to know what the angular position of the car is at any given time, so that we may figure out its angular position at, for example, 17 seconds or 25 seconds. To calculate the angular position of the car, we need to recall some important facts. First of all, we need to understand that distance and speed are related. So the distance s that the car travels is equal to the velocity of the car times t. It's also important to remember the arc length formula. This is an equation that you may have forgotten, but it is an important equation that describes the length of an arc of a circle spanned by angle theta. So when the car travels some angle theta, the distance that it travels is simply theta times r. If we equate these two equations together, we get the desired result. Theta is going to end up being Vt divided by r. This equation is important because now we can figure out what the angular position of the car is at any given time, so long as V and R are known. Next, we want to discuss the car's position as a function of time. Remember, this is two-dimensional motion, so position is really a vector. It has an x component and a y component. You should already be familiar with calculating r in terms of theta. You should understand that r has an x component and a y component, and these two components are related to angles by sines and cosines. So we can write the x component of r as r cosine theta and its y component as r sine theta. Except that in the present case, theta itself is a function of time. Theta is changing as the car drives around the track, and we know how theta changes with respect to time, so we're going to substitute this expression for theta into the trigonometric functions. So we can think of the x component of the car's position as r cosine of Vt over r, and the y component, or the y coordinate of the car's position, is r sine Vt over r. We can also draw these vectors, and of course these vectors would just be radial vectors pointing from the center of the circle, from the origin of our coordinate system, to where the car is located at any given instant. Next, we'd like to know about the car's velocity at any given time. We'd like to know how the velocity depends on time so that we can calculate the x and y components of velocity at any given time. Recall that velocity is simply the derivative of the position vector. Of course, the position vector has two components, an x component and a y component, so you will have to take the derivative of x and y separately. So the quantity that you see here is simply v sub x, and this was calculated by taking the derivative of x with respect to t. The quantity you see here is simply v sub y, and this was calculated by taking the derivative of y with respect to t. Recall that the x component involved the cosine function, and of course the derivative of the cosine function is minus sine. And when you take a derivative of a trigonometric function, you also have to take the derivative of the argument, the thing inside the parentheses, and that's how we ended up with a v out front. We can draw the velocity vectors. We remember that velocity vectors always point tangent to the path that is being followed. So if we were to carefully plot these components, we would find that the velocity vector at different times always points tangentially to the circle. Next, we'd like to know about the car's acceleration. Since we know the velocity, we can take another derivative to calculate the acceleration. Recall that velocity has two components, vx and vy, so we're going to take the derivative of the x component. The derivative of the sine will give us a cosine, and of course we'll have to take the derivative of the argument, which gives us a v over r, hence v squared over r. Similarly, for the y component of acceleration, we'll have to take the derivative of the y component of velocity. Derivative of a cosine gives us a minus sine, and the derivative of the argument gives us v over r. Hence, the y component of acceleration becomes minus v squared over r sine vt over r. If we were to plug in several different times for these into these functions and actually numerically calculate the acceleration vector, we would find, as we have already said, that these acceleration vectors point inwards directly towards the center of the circle. Now, the assertion that we wanted to prove was the fact that the magnitude of the acceleration vector is simply v squared over r. So how do we calculate the magnitude of a vector? Recall that to calculate the magnitude of the vector, you take its x component and you square it. You take its y component and you square it. You add those together and then you take the square root. We're essentially applying the Pythagorean theorem to this vector. So finally, what is the magnitude of the acceleration vector? Well, square the x component. That gives us v squared over r squared times cosine squared plus v squared over r squared times sine squared. The minus signs disappear because we're squaring them. And then if you look at this equation for a bit, you'll see that you can factor out the v squared over r outside of the square root symbol, and inside the square root, you'll have cosine squared plus sine squared. Hopefully you remember from your trigonometry days that cosine squared plus sine squared is equal to 1, and of course the square root of 1 is 1. So the magnitude of the acceleration vector, so a without an arrow on it, is simply v squared over r. So this finally proves that for an object in uniform circular motion, the acceleration vector has a magnitude of v squared over r. This turns out to be probably the most important fact about uniform circular motion. As we start doing problems with circular motion, you'll see how this fact comes in to be a useful fact. If you were paying attention to the last couple of slides, you probably noticed that discussions of circular motion are quite complicated because of the fact that there are lots of trigonometric functions everywhere. Keeping track of all the trig functions and their arguments and their amplitudes can be quite difficult, and it can generally become something of a headache when solving complicated circular motion problems. It turns out all of that can be simplified if we adopt rotated coordinate systems. To make that idea more precise, notice that up until now we've been using a standard XY coordinate system. The standard XY coordinate system is a static coordinate system, meaning that its orientation is the same everywhere, no matter where the particle is located. The x-axis is always horizontal, left and right, and the y-axis is always vertical, up and down. So when the particle is here, the x direction is simply to the right and the y direction is up. When the particle is over here, the x and y directions are the same. When the particle is here, again, the x and the y-axis point in exactly the same directions. Nothing changes even though the position of the object is changing. It turns out the radial-tangential coordinate system is a much better coordinate system for discussing circular motion. The radial-tangential coordinate system is a dynamic coordinate system. Its orientation changes as the position of the object changes. As the name implies, the radial-tangential coordinate system is a coordinate system that always points either in the radial direction or the tangential direction. When the object is over here, the radial coordinate system, labeled as RT, looks very much like the standard XY coordinate system. But a second later, when the object is over here, notice how the radial tangential coordinate system has rotated. The coordinate system has rotated along with the object. Notice the r-axis, the radial direction, points along the radius of the circle, and the t-axis, the tangential direction, points tangentially to the circle. A second later, when the object is located over here, the radial tangential coordinate system once again looks like a standard XY coordinate system, but notice how this time the r vector is aligned with the y-axis, whereas initially the r vector was aligned with the x-axis. So the RT coordinate system is again rotating with the object. A second later, this is what the radial tangential coordinate system looks like. In fact, we can draw a radial tangential coordinate system everywhere around the circle, and as you can see, the RT coordinate system is essentially tracking the motion of the object. The r-axis is always pointing along the radius of the circle, and the t-axis is always pointing tangentially to the circle. It turns out by adopting a dynamic coordinate system that rotates in this manner, we can actually simplify many of the equations that describe circular motion. We have claimed that for circular motion, kinematic quantities such as position, velocity, and acceleration are much easier to express in the radial-tangential coordinate system compared to the standard xy coordinate system. To appreciate that fact, recall that in the standard xy coordinate system, the position vector, such as the x and the y components, had to be written as r cosine vt over r and r sine vt over r. The velocity vector has an x component and a y component, and here they are. And the acceleration vector also has an x component and a y component, and here they are. We've derived these. Each one of these is essentially a derivative of the previous kinematic variable. Notice that if you were to memorize all of this, you would probably have a hard time because there's lots of sines and cosines. There is lots of positive and negative signs, and the arguments are not simple, and the amplitudes, the thing in front of the trigonometric function, is different in each case. However, if we switch to the radial-tangential coordinate system, as shown at the bottom two rows, things suddenly become simplified. The position vector does not have a tangential component. It points strictly in the radial direction, and it always has a magnitude of r. The velocity vector does not have a radial component. It's always tangential, and that tangential component is constant in magnitude. Its magnitude is v. The acceleration vector does not have a tangential component, and it points only in the radial direction. It points inwards as opposed to outwards. We call that the negative radial direction, hence the minus v squared over r. Although in theory you can analyze circular motion in any coordinate system you want, as we solve lots more problems with circular motion, you'll quickly realize that using radial-tangential coordinate systems is vastly to your advantage. And that's the end of this lecture. Thank you for your attention.